Welcome back. In this video, we finish 2.3 mathematical induction. Today, we really focus on summation and summation notation. Many interesting identities come about from summations, and these can be proved nicely using induction. So, as a warm-up, let's look at a few summations. On the left, the summation as k goes from 1 to 5 of 2 to the k. How would you write that out? Well, k is the index. K goes from 1, 2, 3, 4, and then 5. So I just put in those different values for k and I add up the terms. Similarly, on the right, can you see what that expression will be? My summand is simply k, so I just add up the terms. 1 plus 2 plus 3 plus 4 plus 5. Here's a slight variation. What if the upper limit is a variable m? How does that change the summation? Well, I need to use dots, the ellipsis, to indicate missing terms, but the pattern continues, 2 to the 1, 2 to the 2, and so on, up through 2 to the m minus 1, and then finally 2 to the m. How about the one on the right? So it's simply 1 plus 2 plus all the way up through m minus 1, then plus m. Alright, one more step. It's often really helpful to pull out the very last term of a summation. So look what's going on here. The original summation takes k from 1 to m of 2 to the k. This new guy in parentheses takes k from 1 through m minus 1. So it stops short by 1 of the last term of the sequence. So basically, I'm just asking, what is the last term of the sequence? If you look at the line above, I've essentially isolated the first m minus 1 terms, and all that remains is 2 to the m. You can think about it this way. The mth term, at the very end, k goes from 1 to m, k takes on the value of m. That last term is going to look like the summation, but just with k replaced by m. Similarly, if I look on the right, I have the summation k goes from 1 to m of k, and in parentheses I only take that summation up through m minus 1, so what remains is the m, and again the last term just looks like when the k takes on the value of m. That's what I get. So here's an example of a summation that has an interesting identity. Let's sum the first n powers of 2. So it's 2, and then 2 plus 4, 2 plus 4 plus 8, 2 plus 4 plus 8 plus 16. So every time I'm adding one more power of 2. And the results I get look like this. Do you see the pattern there? Well, you might notice 62 is close to 64, which is a power of 2. That's why that's an interesting number, maybe 64 minus 2. And then 30, oh, that's not far from 32. Subtract 2. 14 is really 16 minus 2, 8 minus 2, 4 minus 2. So it looks like these numbers I get on the right are really powers of 2 minus 2. In fact, 64 is 2 to the 6th. And 32 is 2 to the 5th. And so in general, the different n values are given on the left. So for example, here I might have, this is n equals 4. I'm summing 4 terms. So when n is 4, my expression looks like 2 to the 5th minus 2. And the last summation here, that occurs when n equals 5. And the closed form I get is 2 to the 6th minus 2. So in general, what does this look like? The summation as k goes from 1 to n of 2 to the k is 2 to the n plus 1 minus 2. Whatever that n value is, however many terms I'm adding, I add 1 to that. That's my new power of 2, and I subtract 2. Well, this is just a claim. This is just a guess. I've not established that this is actually true, but it appears to be true. So now, with induction, let's prove that it's true. Claim, for all n greater than or equal to 1, the summation as k goes from 1 to n of 2 to the k is 2 to the n plus 1 minus 2. Let's prove the base case. We'll just put in n equals 1. Now, the summation when n equals 1 is a very boring summation. It is only one term. But the summation evaluates to 2, and the closed form evaluates to 2. It's the same number, so that's good. That establishes our base case. The claim really is true when n equals 1. Now, let's assume, here's our induction hypothesis, let's assume that for some m greater than or equal to 2, the summation as k goes from 1 to m minus 1 is 2 to the m minus 1 plus 1 minus 2. You see, basically all I've done is take the claim and substitute m minus 1 for n. Where I had an n before, that becomes m minus 1. Where I had n plus 1, I have m minus 1 plus 1. I'm just substituting m minus 1 for n in the original claim. So I'm assuming that this summation actually works. Let me just simplify a little bit that exponent there. And so I get 2 to the m minus 2. Well, now what? Now I want to establish that the summation going all the way up to m actually satisfies the closed formula as well. So I do the trick like on a couple slides ago where I pull out all the terms except for the last term. So I take my summation up through m minus 1, and then I have to add on the last term. So in this case, the last term will be 2 to the m. So I've split my entire sum up. So this equality is maybe by the property of sums. I'll just say by sums. It's how summation works. But now what can I do? The stuff that I've put in parentheses, that was what I had under my assumption. By the induction hypothesis, so by assumption, I know that this summation that goes up through m minus 1 is really 2 to the m minus 2. And now we just do some algebra. And I end up with 2 to the m plus 1 minus 2. Well, that's exactly what I wanted, right? Because I had assumed that the summation works with m minus 1, and now I just showed that under that assumption, the closed formula also works with m. And this establishes that the summation as k goes from 1 to n of 2 to the k equals 2 to the n plus 1 minus 2. That thing is true for all n greater than or equal to 1. So just to run that through very quickly, remember, I show that the closed formula works with n equals 1. I assume that the closed formula works when I sum up to m minus 1. Under that assumption, I prove that the formula works when I sum all the way up to m. Therefore, I know that the closed formula works when I sum up to any number. All right, let's try some more. Here's another claim. The claim is that the summation as k goes from 1 to n of k is n times n plus 1 over 2. So pause the video, give this thing your best try, and then when you're ready to check your work, unpause it, and we'll see how you did. All right, go to it. Let's take a look. So for the proof, I will start off with the base case. Let's observe that when I sum up to 1 of k, I just get 1. And also when I plug in 1 into the closed formula, I also get 1. And so the equation holds for n equals 1. Now let's assume that for some m greater than or equal to 2, the summation up to m minus 1 follows the closed formula. So I substitute m minus 1 for the n. And I simplified a little bit there. That m minus 1 plus 1 just turns into the m at the end there. All right. Now let's take the summation all the way up to m. I will break it apart. I break it into all the terms except the last, plus the last term. But I know something from my assumption about summing up all those terms but the last. That is m minus 1 times m over 2. That was my induction hypothesis. Do a little algebra, simplify, simplify, and look what we get. So previously I had assumed that the formula works with m minus 1, and then I show that the formula actually works also with m. Since the formula works for 1 at the very beginning, now I know this formula works actually when my upper limit is any integer n greater than or equal to 1. Okay, for the remainder of this video, I'm asking you to try 3 different induction proofs. On subsequent slides, I will go through the proofs of these 3 claims, but really give it a try. Pause the video, try your best, and then see how the proof unfolds. I will display the proofs line by line, so even if you just have a start, maybe see the first few lines of the proof and then pause it, and then see if you can finish it up. Just as an aside, before we go through those proofs there, it's interesting to note that induction is good for verification of a claim, but not for discovery of a claim. These closed formulas that I present here, how in the world would you come up with those based on the summations? And induction does not help us make the claim. A lot of guesswork and trial and error and some insight and pattern recognition is required to make a guess. But then induction is really useful once you've made a guess to verify whether that guess is right or not. Okay, that was just my little aside. Give these things a try. Go ahead and pause the video now and work the proofs as you can. Good luck. Here is the proof for A. Here is the proof for B. And then the proof of C. And that finishes the proof of A, B, and C, but I want to take one closer look at part C again. This is an interesting claim, and there is an alternative proof for this that's pretty slick. So take a look at that summation. That summation is really 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4, on and on and on, all the way up through 1 over n times n plus 1. Now, each of these terms can actually be expressed as a difference. This 1 over 1 times 2 is really the same as 1 minus a half. 1 over 2 times 3 is the same as a half minus a third. 1 over 3 times 4 is the same as 1/3 minus 1/4, and so on. You can pause and verify that if you want. Just kind of think about that. And we have a telescoping summation. This is amazing. Look at this. I have a negative 1/2 and a positive 1/2. I have a minus 1/3 and a positive 1/3. A minus 1/4 and a positive 1/4. So in fact, all those terms on the inside cancel out, and all I'm left with is 1 minus 1 over n plus 1, which is n over n plus 1, which we had hoped to establish. So I kind of like this proof. It's very clever, it's pretty quick, and this is definitely a non-induction proof. All right, this finishes our section on induction.